I'm going to be talking about the FPGA-based MIDI synthesizer with touchscreen wave shaping, supervised by Daryl. Just quickly what I'll cover, I'm going to go briefly over the context, I'm going to give a design overview, I'm going to talk about how I implemented it and what results I got. So, just a brief recap on what I spoke about last semester in terms of the shape of the industry. As you can see, synthesizer industry alone is worth more than $100 million worldwide. People spend a lot of money on synthesizers. $1,200 per synthesizer is the average price paid, and some go up to $3,000 easily. And then I did a quick survey of Kickstarter, and just to show, since coming in, you can see that people spend a lot of money on them, even when they don't particularly have many innovations. They just knock off some previous synths. And then I'll talk about a couple of trends in the industry. The first one is that we are moving away from the keyboard. We're moving away from usual ways of interacting with music and moving more towards different, more organic ways, such as Imogen Heap's accelerometer-based MIDI controllers, or this tactile table with RFID blocks. Another trend is wave shaping. Wave shaping allows you to get in and actually manipulate the shape of the wave directly. This is normally mathematically defined. So I just made a quick mock-up here. This is a common wave shaping tool which simulates crossover distortion, and it's just taking a sinusoid to the n. In this case, it's n is 5. The problem with that is it can be clumsy. You can not necessarily know what the result's going to be or how to arrive at a waveform. It's computationally intensive often, and it can be slow and finicky and slow down creative flow. So my solution is direct touchscreen wave shaping. Rather than starting with a sine wave and then manipulating it to change the wave shape, with this you just draw a wave directly onto the touchscreen, creating whatever sound you want. You can also modulate it in various ways also by drawing waves on the touchscreen. So here's the design. You can see the touchscreen in the center. You can draw a wave in the drawing position. There's a bunch of touch buttons down the side. And then there's various buttons you can push to move between modes to do various different types of modulation. And there's the VU meter in the corner, just tells you how much volume you've got. So for the hardware part of it, I just designed a breakout board for the Z board, which is a Zinc FPGA board. So I connected everything to an FMC connector. Rotaries and buttons go in. The touch controller talks to it via an I2C buffer. And then I've got 32 bits of other buffers which talk to the VGA out, the VU meter out, and the MIDI input in. So MIDI is musical instrument digital interface. Rather than having to send full musical waveforms, we can just send a 3-byte command which is note on, note pitch, and note velocity. That obviously means it's much less data intensive, and also means that you can plug any MIDI controller into any device, because they all work together. So system level view, I've got the MIDI input and the rotary buttons coming into the FPGA. I've got the touchscreen which talks to a touch interpreter so that you can draw things on, which then once you've selected a waveform moves to a DDS-BRAM. The DDS-BRAM also talks to the graphic generation to display the wave on the screen so you can see what you're drawing. And then the DDS also talks to audio generation, which takes a feed into the MIDI interpreter. The MIDI interpreter gives it a number that is necessary for it to step through to get the note that you want, based on which note you select on the MIDI controller. And then it's processed by a bunch of different processors that you can choose, and then comes out through the DAC. So, the main oscillator is the first step in creating a sound. You draw any sort of waveform. There are typical waveforms, sine, square, saw, etc. on the side that you can just bring up, and then a bunch of parameters down the bottom that you can change with rotaries. Every point in that, it gets scaled to 512, so that it can sit as the lookup table for a DDS. It then, takes the MIDI interpreter number and scans through at the necessary speed to produce the sound. Then there's the frequency modulation section. It turns out that if you frequency modulate a signal at audio frequencies at an integer multiple of the fundamental, you get some really interesting sounds, some really nice harmonically rich sounds. They can sound like real instruments, like trumpets or something. And there's a funny naming convention in the industry because it's frequency modulation is what consumers look for, but it's actually implemented as phase modulation. In my thesis, I go into how under certain conditions they're actually the same thing. Don't have time for that now, but the only difference is the coefficients mean that it scales differently. The bandwidth of the side lobe scales differently with frequency. So then there's envelope. Old school synthesizers, you push the node on, it's full, you take the finger off, and it goes full down. Obviously, real sounds aren't like that, real instruments aren't like that. Real instruments have a transient, followed by a sustained level, and then when you take the key off or whatever, it drops to 0. So I've implemented it so that the MIDI velocity comes in setting a full scale, the transient hits that, drops down to your sustained level, and then when you take it off, then it goes down. Then there's the filter. I opted to use a biquad filter. The benefit of a biquad filter is that it's useful. You can set it different coefficients and get about 10 different filter types out of it at any frequency cutoff you want, and a wide range of different resonances and Q values. And it's quite computationally simple, as you can see in the diagram. Yeah. I've implemented low pass, high pass, and band pass filter. And then there's a low frequency oscillator, which is a sub-audio oscillation, which you can draw on the screen again to make whatever you want. And it just addresses a different parameter in the system. So for instance, you can change the oscillator amplitude, which just basically is slow AM. You can oscillate pitch, which is just slow FM. And then frequency cutoff, you can chain LFOs to get crazy, unexpected movement of different modulations, because you're modulating the modulator or something. And then there's the effects block, which at this time is not really working. But what I've put together is Bit Crusher, which is a quantizer. Basically does 1-bit quantization, which some people like. And a delay, which is just a repeat of the signal that's delayed and added back to the original signal. And then some portion of that is fed back into the input to create repeating delays. Okay, so I'll talk about what worked and what didn't. So the goals I set up at the start of the year, I designed the FMC board successfully, I designed the MIDI interpreter, I interfaced with the onboard DAC, and I implemented an arbitrary DDS, so that all happened. Second semester, I implemented additional audio components, I built the enclosure, I finalized the graphics. I'm not a graphic designer, they're still a bit wiggly, but I'm pretty happy with them. And build a new output stage, I decided I didn't need to because the Z board stack was totally sufficient, more than sufficient for what I needed. Then the secondary objectives, build a standalone board, didn't get to that. Design additional audio components, I did some. Select a different DAC, like I said, unnecessary. I'm creating more noise in other places than the DAC is producing. Implement polyphony, didn't quite get there, and I put an analog VU meter in it so you can see how loud you're being.
2 minutes.
2 minutes, cool. What I think was good about it, it can create a huge amount of different sounds because you can chain things together in all kinds of different ways, and because you can draw any waveform, you can get any kind of crazy sound. It's difficult to get the same sound twice, actually. It can get frequencies. It can get frequencies within 0.2 hertz of the desired. So if you play A440 on a keyboard, you get A440 out plus or minus 0.2 hertz, which is great because then it will be in tune with everything else. And it's really, you can really creative and intuitively experiment with it. You can just you can really think about what you're doing, or you can just paint and see what happens. And there's a couple of small issues. It has a bit of harmonic distortion. I could have filtered that out, but if I'm filtering the top end of a wave shaper, and losing that harmonic content, then there's not really any point of having the wave shaper. And the distortion actually sounds quite pleasing to me. And so, yeah, so it was a trade-off, and I decided to go with what sounds better. And there's still some work to be done to get it to the level that I want. Some minor niggling issues. So in conclusion, I think it's a pretty cool synthesizer. And I think with a bit more work, I can get it into something that I'll use often. Thanks.
Questions? Yes.
What is your definition for the total harmonic distortion?
My definition, like how much there is? It's 1.36 is the ratio. but it still sounds like a sine wave. And like I said, I could filter that out. And in fact, if you use the filter block, you can filter that out. So I left it up to the user, I guess, as to whether they like the distortion or not, because it is possible to filter a lot of that out using the filter block, rather than me pushing the filter.
I guess what you want to do is to create some sort of crazy sound effects.
Yep.
So the total harmonic distortion is irrelevant.
Yep, it's very good at that, yes. Yeah. Yeah, I think it's more useful in terms of sound design, like synthesizing sound effects and kind of scores for video games and stuff, than it is for playing in a rock band. It can get. I made an explosion the other day. I made the sound of when you get a phone too close to a speaker in GSM, and a tick 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 tick. You got that perfectly. I knew I want to stop with it. Yep.
You said it's find it hard to reproduce the same sound twice, so you have a way of recording. So if you go, oh, I like that one, and can I store that one away and then bring it back in?
I would like to implement that, but there's so many features that I've had to do. It's just a limit of time.
Is it something you put on Kickstarter yourself?
No, but if people like it, I might think about it. Obviously, it'd still take a lot of work.
Any more questions? Okay, well, thank you very much.